Welcome everyone to the webinar, How and Why You Should Form a Materials Informatics Strategy. I'm Mike Holman, the VP of Research here at Lux. I'm moderating today's session, which is going to be led by our speaker today, Zhao Zhang, an analyst on our materials team. We're going to get started here, but at any point throughout the webinar, type any questions you have into the question box on your screen. We'll answer as many questions as we can at the end, time permitting. But if your question doesn't get answered or you think another one up later, please don't hesitate to email it to questions@luxresearchinc.com and we will respond. So at that point, let me turn it over to Zhao Zhang.
Okay, hello everyone. So thank you, Mike, for the introduction. So for those of you who know me well, so I can talk about materials informatics all day, and certainly I'm very excited to talk about the how and why you should form a materials informatics strategy at this point now. So at Lux, we have been tracking the progress of this technology in the past few years. We have certainly seen the progress in the space. Started from just drawing the landscape, maturing the technologies to this point where we think it's time to think about how to form your own materials informatics strategy. So before I really get started on the agenda, I want to show you two heroes of mine. First one, Thomas Edison. So everybody knows Edison. He's really famous for his great inventions. In fact, he has over 1,000 patents that literally changed our world for the better. So, and amongst all these great inventions, you could probably argue that the greatest one is the light bulb that he invented. So that's why I chose to show this picture of Edison holding one of the light bulbs he invented. So what you probably don't know is that in order to be able to find the best material for the light filament, which is tungsten, Edison tried over 3,000 materials before finding tungsten is indeed the best one. So that's lots of time, lots of effort, but this is Edison we're talking about, and he was able to get it done, lots of endeavors. But now, we have computers, we have AI tools, we have digital tools here. The question here is that can we do it better? Can we do it faster? And also, don't get me wrong, Edison is a hero of mine, but I would still want to say that are we sure tungsten is the best material, or tungsten is just the best material of the 3,000 materials that he tried, right? So that's before the computer age, so he was able to do everything he could. But now I want to show you another example, which is another hero of mine, Tony Stark from Iron Man. So of course this is fictional, but in this movie, Tony was able to use some of the digital tools, I like to call it materials informatics, to first discover a new element called vibranium, and then he actually went ahead and used vibranium-based material to build the energy source for his suit. So I don't know how much time it took him to do this, but in the movies it took a few seconds. I'm assuming it's weeks in the movie. So why am I showing you those two cases here? Well, because you can argue that the holy grail of materials innovation is to help us move from Edison to Stark. And of course, we're far away from the Stark age, but we just passed the Edison age. And I can argue that in order for us to do that, or to accelerate the pace toward Tony Stark, materials informatics, it's a crucial technology for us to think about and engage now. Okay, now let's go back to the agenda, right? Today I want to talk about materials informatics strategy. First, I want to talk to you about why you need a strategy, and then second, I want to talk about how you form a strategy. So in this section, I will talk about three strategies that we propose, and we have seen some examples. I will provide some analysis, comparisons to show you which one of the three is the best in terms of data efficiency. And to conclude today's talk, I want to talk about some points about how you execute the most data efficient materials informatics strategy. And there's no way I'm not going to talk about the future, which is outlook and my favorite part. See what's going to happen if everybody's thinking correctly about the materials informatics strategy. Okay. Okay. So why do we need a MI strategy here? Well, So go back to ground zero. So what's the problem, right? What's the problem in the materials space, right? Why did Edison, take so long to find the right material or to develop any material? Because on average, a new material development takes about 10 to 20 years. That's very long and it's very costly. We got to do something about that, right? To give you a concrete example here I'm showing you a comparison in terms of the timeline for airplane development versus airplane material development. This is from a report from the U.S. Office of Naval Research. So as you can see here, it takes about 5 to 7 years to iterate and develop a new component of an airplane. And in order to do that, the beginning stage of that development cycle is to iterate on the right material to use. And in order to be able to hit the 5 to 7 year target, ideally you take about 2 to 3 years to identify the right material to use. And now you can see in reality this is far away from the truth. It takes about 8 to 10 years. And if you still remember my last slide, on average it takes about 10 to 20 years. So now we got a problem here, because materials development is so slow, at least in this case, it's slowing down the downstream product development cycle as well. So what should we do here, right? Not surprisingly, we have seen government initiatives around the world trying to do something, right? So I will talk about more government initiatives later, but President Obama actually launched the Materials Genome Initiative, the MGI, in the US in the year of 2011. So basically, the goal for MGI here is to use materials informatics. So just to quote his speech, with the digital tools and the computational tools and experimental data, we should be able to shorten the materials development cycle by at least a factor of 2 through collaborations, right? I'll talk more about other government initiatives later, but now I want to talk to you about, hey, what is materials informatics, right? So we talk about there's a problem for materials development, it's taking too long. We talk about some comparisons, we talk about some government initiatives. Now, what is materials informatics? So a simple definition here is shown there on the slide. It's to use artificial intelligence technologies to accelerate chemical and materials development. And there's lots of benefits we can talk about. I'm just going to list 3 of them. First of all, think about using materials informatics to improve the R&D efficiency for chemical and materials research. That's going to shorten the timeline. Second, think about using materials informatics to extract additional value from existing data, whether this data is coming from experiments or it's coming from a computation or coming from both. And last, certainly not least, think about materials informatics to improve your DOE efficiency, design for experiments, so that now you're only doing the experiment that matters. Every data point counts. Okay, and here on the right side, I'm showing you one typical example of a materials informatics project. In this case, it's done by UCSB. They're trying to use AI tools to select the best material in terms of a given electroresistivity. Okay. And so at Lux, talked about, Lux has been tracking the progress of this technology for a few years. One of the research tools that we use is called the Lux Tech Signal, which is our own data-driven tool to analyze innovation interest of a given technology. So just a quick refresher for some of you who may not be that familiar with the Tech Signal. It uses publicly available data sources like papers, patents, government funding, and VC funding, combining those data with our own data based on primary research interviews to give you an indication of a certain technology's innovation interest in terms of years. So here, I'm showing you a comparison, right? So on average, compared to those average emerging technologies, we have definitely seen an exponential growth of materials informatics innovation interest in the past 4 or 5 years. There's lots of momentum there. I will talk about some of there today, but more to come. Okay, so I talked about the US MGI. Like mentioned before, the MGI it's a multi a government agency initiative in the U.S. Certainly, it's not the only one in the world. So, I'm showing you a few examples of government initiatives around the world. You see, there's China building materials data sharing facilities around the country. You see, the Japanese government, NIMS, which stands for National Institute for Materials and Science, building databases for different materials as well as building centers. And also in Europe, we have NOMAD, which is a center of excellence leveraging materials informatics. And also at the bottom, I'm showing you a typical project dedicated on metallurgy to use materials informatics to accelerate the development cycle. So the basic message here is clear, right? Materials innovation takes a long time, and materials informatics is promising too. And governments around the world have seen the potential. That's why there's supports from them, building the necessary infrastructures and the centers, and collaborations. So the infrastructure has almost been built. Of course, there's more progress to come, but I want to make sure this is clear. So we have the government support, and we're using materials informatics around the world. Now is the time for you to think about how you should leverage this to form your own materials informatics strategy. Okay, so I talked to you about what is materials informatics. Now let me talk to you about how does materials informatics fit into the existing paradigm of experiments and simulation and computational tools there. Okay, so it all begins with the experiments. Well, it doesn't need any explanations. You try things out. This is the Edison approach. And but now that we have computers, let me translate that modeling and simulation definition, right? So you are using computers plus physics to do experiments virtually. So of course the benefit is that, hey, it's much quicker. But of course, at the trade-off here is that it's a few things, right? Yeah, you got to use computing power, and sometimes a really complex simulation can take a long time, lots of computing power, and also accuracy. There's a balance between how much physics you put in. You cannot put every physics in, and also how much computing power you need. But these tools are complementary. They're generating data, whether experimentally or computationally. And I'm going to pause here, right? Because people can argue, of course, actually through my interactions with people from companies, people think we're at this point where we have experiments, modeling, and simulation. But I like to argue that we're now just entering into a new paradigm where we have materials informatics coming to play, forming this triangle of this paradigm. So with recent developments from, from AI technologies, from, let's say, computing power, like GPUs, and also cloud computing, finally we have the tool and the force, computing power, to power up materials informatics. And it's going to change this new paradigm. It's going to be complementary with both experiments and modeling and simulation for that matter. So in a sense that you can think of using MI to analyze the data provided by those two components and generate feedback to, to create a positive feedback loop for those two components. So how do we do that? We need data, right? So data sits at the center of this new paradigm. It's very crucial to power up materials informatics to get this new paradigm, triangular paradigm going. And definitely data is not, just important, but also, there's some challenges there brought by data as well in materials informatics. So here I want to, there's lots of ways and lots of research articles talking about the data challenges in general, and some of them are actually dedicated to materials. But here I want to talk about the data challenge from three perspectives. First of all, I want to talk about data quantity. So you may be wondering, what is this logo here? That's from YouTube, right? So YouTube video streams about 4 billion hours of video data per month. That is roughly equal to 6 million terabytes of data. And the Materials Project, which is one of the most well-known openly available materials database in the space, a typical data set of DFT data, which stands for density functional theory, computational data. A typical data set, it's about 130 1,000 DFT data points, that is only equal to roughly about 5 terabytes. You do the comparison, we need lots of more data. So this is actually in general the case for materials space. We need more data, and it's very costly to get additional data. Well, oftentimes you have to do experiments and very expensive computations as well. Okay. What about data quality, right? So, research data from the materials space, it comes in all kind of, formats. Here I'm showing you some typical ones. You have PDF, you have handwritten version, which is sometimes hard to recognize. I was a graduate student before. I know how terrible the handwritten ones can be to recognize. And also, at the bottom, I'm showing you an image of data, which is, for some of you know, this is unstructured data. And there's many more types as well. So the central pain here is that you need to standardize all this data in the same format to be able to use materials informatics, and data standardization. It's a real problem there. It's very hard actually to do. Last but certainly not least, it's about data sharing. So this is rather cultural than technical, right? So here I'm showing you 3 companies, not because I don't like them. In fact, I like those companies very much. These companies represent 3 typical large chemical and materials companies that, on the surface, they may not have the incentive or motivation to shake hands and share data. And so what happens for the industry here is that people from different companies are doing experiments that other people have done already. So if you take a look from the industrial perspective, this is a waste of resource and energy as well as time. So we got to think about create clever ways to push the boundary here. But data sharing is also another challenge there as well. So because of these challenges we talk about, we do think that corporate players really need to think about an effective materials informatics strategy to be able to correctly and appropriately assemble their data to realize the full benefits for their companies. So therefore, I think you need to form a materials informatics strategy, and also one more component, as I will talk about later. So we have seen a few, despite the challenges we have seen a few early adopters in the chemical and materials space forming their materials informatics strategy. And because of the data-centric nature of this technology, we do think that early adopters will have a first mover advantage only after they can successfully overcome the steep learning curve of this technology. But you need to think about how you form your own materials informatics strategy now, otherwise you're at risk of being left behind. Okay? Yeah, so hopefully at this point I convinced you there's a need to think about an MI strategy. The second part of the story, I'm going to talk to you about how. How do you form one? So this is a slide showing you some known materials informatics partnerships. As you can see, I don't know what's your feeling, but when I see this, I feel like this is very incomplete. I'm sure there are many more there, and also that it's very fragmented, which suggests new opportunities for players to get involved. Okay, so I will walk you through this, this partnership map, and I will identify through the looking at this partnership map to show you that there are 3 strategies there. Let me get started. So the first one here, you highlighting Citron Informatics, which is one of the lead MI startups in the space, is to work with the startup company, right? So you work with the startup company, it's definitely the quickest approach to get involved in materials informatics. So the basic approach here is that it's by contract. You present a problem, and you have to share your data, and then the company is going to use their platform to help you solve the problem for a contract fee. So this is really good if you want to just get started, and also you have a project that has a very tight deadline. But like I mentioned before, to do this, you're gonna have to share some of your data with the startup. So if that really concerns you that much, think twice. So no further comments on this strategy here at this point, but I do want to clarify something. So most of the MI startups, in fact, actually all the MI startups that I've talked to, they're saying that they're not using data they got from prior engagements from former customers to train their model and benefit their future customers. They're only keeping the resulting software architecture based on prior engagements. So not the data. So what does that mean here is that in theory, future clients will not get a data advantage over the previous ones. So I think this is very important to clarify because oftentimes I heard some misunderstandings before. And give you an example. So BASF is working with Citron Informatics to using their AI tools to develop new environmental catalysts for CO2 capturing reactions. So in this case, BASF shares some of their catalyst experimental data for Citron to use their platform, which is called Citronation 1, I think, to do high throughput screening for potential catalysts. And according to BASF, this approach has been accelerating their progress. So I thought this is a good case in point. Okay, so second one, I'm highlighting a few individual companies here because these are the companies that claim to have started their own internal MI initiative. So this means that you hire the right people or develop internal talents and to form an internal MI initiative to develop your own MI platform internally. So this approach definitely eliminates the data sharing concern. You don't have to share data with anyone else, outside of the company. But and also, if you're a company that has lots of potential talents and decades of data, this is maybe a good approach for you to think about. So, but the downside here is that, as far as I know, I don't think there's any university programs offering a PhD program called Materials Informatics. It's a new field. In fact, just a word on the MGI. Part of their goal is to develop the next generation workforce. Basically, we need people. We need the people with the right talent. So finding the right people to assemble your team can be tough. And also, if you're not that financially stable, you may run into a problem because of the trial and error stage. Oftentimes, costs lots of upfront investments. So think about you're a large company that has lots of data. Also, you're financially stable, or maybe you're working on a highly specialized material. So this may be beneficial for you to think about. Okay, and here I'm showing you a few examples. Companies claiming they have their own teams. Besides Tesla and SpaceX, all the others are Japanese companies. The Japanese companies are very active in the space. Okay, so the last one, certainly the most radical and interesting one, forming a consortium with your peers. Right. So this means that for a company, you work with other companies that you can see data synergy to form a consortium or join a consortium led by a trusted company or a government group. So think about you're a company that doesn't have sufficient data, and also you do have data synergies with many other companies. This is maybe your approach to go. But if, like I said before, if you have lots of data already, or if you're developing a new material, sharing data can be less helpful, but there's still some benefits. I'll talk about that later. So think about you are a mid-sized company that individually doesn't have enough competitive advantage with the leader in the space. Think about joining a consortium to compete with a leader, and this is going to be able to give you an edge on them. Okay, so several examples here. IBM's Research Frontiers RFI Institute has a consortium. So they have 10 projects, including accelerated materials discovery, which is materials informatics. So they use IBM's computing power and expertise to work on MI challenges. So here I'm showing you 6 member companies on the consortium. So they can choose to share data with IBM and each other. Although now they do have another offering that they can just engage with IBM separately on individual projects. One more consortium here. It's started by the Japanese government, NIMS. NIMS formed a consortium with 4 Japanese companies 2 years ago to work on a platform called Materials Open Platform, which is on polymers. It's used materials informatics to start gathering data on polymer structures and properties to work on to use materials informatics. Okay. Yeah, so I talked about the 3 strategies before. Now let's put them together and compare. So like I said before, if you just want to get started, working with the startup is the quickest approach, but it definitely presents a severe data security problem. So in order for you to get away with that data security problem, starting an internal MI unit sounds like the better approach. It's indeed a better approach if you talk about data security, but like I said before, be mindful about the potential upfront investment. It's going to be huge. So that's why, with all things considered in terms of data and investments, we do think that the consortium idea is the best way of leveraging materials informatics. In fact, it is the most data efficient way to do it. And that's our conclusion, right? So the last part of the story, I want to talk to you about how do you form a consortium, how do you execute one, right? So I was at a conference in Chicago last week. It's called Materials Informatics for Industry. So we actually, in fact, we co-organized that event with the MGI office director. So this is definitely the topic of that day. We talked about a few consortium ideas, and I presented this this example. Basically, we can learn something from the pharmaceutical space. The pharmaceutical space, it's also highly has high risk and high reward, but people in that space have for some reason are more open-minded to collaboration. That's why the consortium idea in their space is not new. There's numerous consortia formed in the pharmaceutical space. Here I'm just showing you one example formed by the FDA. It's called Critical Path Institute, CPI. So it has 6 consortia at least with over 1,000 scientists, and from governments, from foundations, as well as from 41 major pharmaceutical companies. So I can show more examples, but in general, the message here is that there's always government support and it's always multi-stakeholders. Okay, so how do we execute a successful consortium? Well, the simple answer is that nobody knows for sure in the materials space. But what I do know here is that you got to make sure everybody's interest or incentive is well aligned. To do that, you need 3 things. First, I think government support is very important because the very idea of a consortium is data sharing. You got trust. You got to have the trust, and having a third party, neutral party, a government agency representing the foundation of the consortium, it's really the key. And also, to begin the consortium, think about you're going to need a pre-competitive agreement to carefully define the scope of the project for you to get started. And needless to say, effective IP strategy is crucial as well. You need to be able to give some IP privileges to the members versus people outside of the consortium, but not for too long. Think about those three points. I think they're really crucial there. And also, to conclude the story, I think lessons learned from the pharmaceutical space and some early examples from the materials space. I do believe that the consortium model, which represents an open innovation mindset, it's an evolution to our space and maybe potentially beyond. Think about like I said before, a few mid-sized companies that are working together to compete, so that they will be able to compete with the leaders in the space. Now, who's going to be the new leader? We don't know, right? That's why it's interesting. It's better for the industry. We're going to see some potential competitive landscape reset for the better. And also, I've always just talked about forming a consortium with your peers. But how about think about cross value chain collaboration? BASF, working with Toyota, like just an example, right? So I can definitely see the data synergies between one materials vendor versus a materials user. So that's going to change some of the value chain structure. And just to get things more interesting, think about the idea of having third parties like startup companies or software giants to join as well, so that they can be part of the game, they can provide the technology. It's going to lead to some business model change for the space. It's going to lead to some value chain structural change, but it's all change for the better. Like I said before, I can talk about this all day, but I guess I will stop here and take some questions. Thank you for your attention.
Thank you very much, Jeff. We do have some time now to take any questions on the presentation or on the general materials informatics space. Just type any questions that you have into the question box. If you type it in there, if we don't get to it on the call, someone from Lux will be sure to follow up with you on that. There's a lot to dig into, Zhao, here, and there's a few questions coming in. But one of the things I'm always sort of interested in here is, you alluded to it a little bit on that last slide, the impact on sort of basically the companies that are material users, so like the Honda or the Canon in the case of the IBM consortium that you showed. Right. What kind of role do you see those companies playing in these type of consortia or in the materials informatics space in general? The companies that are not the materials developers themselves, but those sort of prospective users of materials, and how should they think about the MI opportunities?
Well, thank you for that question. Appreciate that question, by the way. So there's a strange phenomena in this space. We have seen examples of forming a consortium with your peers, but for some reason we're not seeing cross-value chain consortium form, which I think should be more straightforward. So just going back to the question, if you are a materials developer, sure, by all means, you're thinking about the data from your company means the materials property data, right? But you are like a materials user, and definitely, you get a lot to say about, hey, I want this material to have this property, behave like this at this temperature. Can you make one? So as far as I know, there is not a effective communication channel between those two parts of the value chain. And I can definitely see, let's say, Toyota, just to pick one company, talk to a materials developer company saying, hey, I need this application, I need this processing, and can you take those into consideration when, let's say, BASF, you're developing a new material for me? So, if from a data sharing perspective, those people, the materials user companies, are the ones that are providing the engineering requirements, also maybe the processing for the data for the consortium, which I think is very crucial for the whole consortium to work well.
Yeah, that's sort of one of the themes that's come up in I think a lot of the discussions we've had in this space. It's sort of being able to do materials informatics well is about having enough data as you described, having the quality data, but sort of like knowing what the right data to collect is and to be measuring, training these models on and things.
Yeah, exactly. Yeah.
There's also a question from the audience about sort of applications of materials informatics. So is materials informatics advanced enough to predict the properties of polymers and composites, which involve longer range molecular interactions, or is it applied mostly for organic materials?
I love that question. I do. Thank you for asking that question. So the answer is that it's still at early stage for at least for polymers and composites. So if you ask me that question, hey, like which field of sub-materials has seen the most progress in materials informatics, the answer is definitely metal. There's several reasons, right? We have the database on metal. It's relatively easy to get additional metal data, but I can definitely see that there's lots of interest in using materials informatics for let's say small molecules and even like large molecules like polymers. I think for small molecules it's okay, it's getting there, but for polymers, I've seen a couple of startup companies trying to develop their technologies, but I don't think it's as mature as the other space. But like I said before, it's actually it's not about what material we're talking about. It's about how much data you have. right? So let's say if you're a polymer company, really had decided to, hey, I want to work on materials informatics for our polymer products, and you do have the data, by all means, try, and you're going to see some progress that you're going to give you some advantage over others. It's more about the data than the material. Okay.
A couple of sort of related questions that I think were probably provoked by that comparison you showed with YouTube and the DFT data.
Yeah.
So what is the sort of amount of data in order of magnitude that's needed for MI, or is there even sort of proof that enough data even exists out there in order to really make MI work effectively?
Yeah, definitely enjoy this question. So the simple answer is that there's no standards. It all depends on what question, what problem you're talking about, right? If you're talking about a formulation, so there's a company called Uncountable. It's a startup company using MI techniques to optimize formulations. So their key differentiator is that they are able to use a very small amount of data points to do formulations. We're talking about 25 trials. Right, we're talking about 40 trials, and that's really small. And it depends on the specific application. And on the other hand, let's say the example I showed you before, the 100,000 DFT data points, that's considered as small. So there's no standard and in terms of data quantity. But generally speaking, for the materials space, we always need more data. So that's why I didn't have a chance to talk about. So there is a trend of using simulation and computational tools to generate data. They call that data imposter, to fill the gap between materials informatics and physical experiment. That's why the triangular paradigm, it's really the key there. Yeah.
All right, I think we've got time for one more question, and which is maybe a good one to wrap up on. Sort of is, how do you, as an organization, maybe check or evaluate that using materials informatics is actually an efficient way to do R&D compared to not using it?
Yeah, this was actually, indeed, that's a very good question to finish the session, right? Think about trying, be more open-minded, and start small, right? So a typical company may have over 10 business units. You don't have to get involved with every business unit, but think of, be more open-minded, think about trying and, do comparisons. But I do want to tell you that, there's some real pain across, individual companies, different business units about data standardization. So be mindful when let's say you try it with one business unit, it works well. When you're, scaling that up to other business units, the data standardization across your internal company can be a challenge as well. In fact, I've heard people talking to me about, hey, I'm a data scientist. I spend maybe 80% of my time standardizing or cleaning my data, and the other 20% it's using my AI tools to make sense of the data. So you got to be more open-minded and think about trying small, but also be mindful of the potential challenge presented even within your company.
Yeah, I think that's something we hear a lot, and our colleagues on the Lux digital transformation team will talk a lot about that with these type of digital transformation tools in a lot of parts of the enterprise. Start small, find some opportunities to get some wins, and get yourself going.
Yeah, definitely.
Okay. All right. Well, thank you very much, Zhao. That concludes the webinar for today. Thank you all for joining us. The slide presentation and the recording for the webinar will get sent out to all the attendees on email today. After you leave the webinar, you will be prompted to complete a survey. Please do take a couple of minutes to fill that out if you can. We really appreciate the feedback, and that helps us to select and improve future webinars as well. But thank you all for joining us, and have a great day.
Thank you.